ARM exploits. You get an ARM machine running by having either ARM hardware like a Raspberry Pi or a Mac M1 or M2, or you run an emulator in QEMU, which is, you can just download an Ubuntu machine I made. It runs on Intel and emulates ARM, emulates a Raspberry Pi, and you can emulate 32 and 64-bit ARM to play with it. In ARM, this is the QEMU command to get the ARM machine going. Once you're in, you name, and you'll get ARM v6L. So that's ARM, and I think this is ARM 32. Yeah, that's what 32-bit ARM looks like, ARM v6L. So you connect to the emulator, and it's a Raspberry Pi, Pi at raspberry.com. It's an emulated Raspberry Pi. And now you make a vulnerable program, and here I made it so you enter the password in hex, so you can put in null bytes and everything. Because I was having enough trouble making the exploit, I didn't need to like dodge bad bytes or anything. So it can take an even number of hexadecimal characters and dump them right in memory for you. So this is the same program we had before. It runs test password and prints some addresses, and here it has a 10-character password, and it copies the data into the 10 characters without regard to length. So you have an overflow here. So you compile this thing for ARM and disable ASLR as before. And now you can fuzz the program, but when you're fuzzing it, you have to give it complete bytes. These are hex bytes, and it's best to give it 32-bit words. Every instruction in ARM is always 32 bits long. They do not vary like they do in Intel. There is a thing called thumb mode that's 16 bits long, but the normal way is 32 bits long. So here's a series of instructions. And also, I think it doesn't like things that don't come out in even multiples of 4, interpret them as addresses. That's why I used this instead of just AAAA, BB. These are things that it will typically accept. So you put that in, you get a segmentation fault. Now you can view the overflow, and it overflows with 202021C. So here it is, 202021C. That's the data that ended up in the instruction pointer, which is called the program counter in ARM. So you can find the return address, and you can see it here. 10828 is the actual next return address after the call to test PW in disassembly. So that's where it is. So now you can spot it on the stack. And there it is. There's the return address. So in 32-bit ARM, it's just like Intel. You have the data you put here, and the return address is down here. So it's really easy. Just put in enough bytes of overflow, and you'll hit the return pointer. So it's the same as what we've done. Now, in 64-bit ARM, they tried to fix that, but they failed. It's pretty hilarious. So let's look at, here's 64-bit ARM. In 64-bit ARM, you compile the same program the same way. You get your ARM64 emulator going. Same program, compile it on 64-bit code, turn off ASLR, and now when you fuzz it, I give it a longer fuzzing, 10, 14, 18, 1C, and so on, and it crashes with a segmentation fault. When you view the overflow, you can find the return address. Now here's where it calls the subroutine. Here's the return address ending in C40. If you look at the stack, C40 is not here. This was the attempt to prevent these overflows. It stores it above here.
So it should be uncallable?
It should be unhittable by the overflow.
Yeah.
So when you overflow, you won't hit it. But the problem is that is the stack frame of the test PW function.
Sure.
Below it is the stack frame for the main function. This is the return address that's used to return back to the operating system. So there is another return address down there. So you don't gain control when you return from the subroutine. You gain control when you return from the main routine, which amounts to the same thing. So you need a longer injection to go hit that address, but you still can do the same thing. So it's pretty hilarious. Anyway, that's what you get with ARM, and you can do that here with an ARM emulator.
Sure.
And you can do the same thing with RISC-V, which is really very much like ARM. Here you just set up the RISC-V emulator, and here you exploit the same overflow. And on RISC-V, it looks very much like ARM code. It's just the open source alternative to the proprietary ARM. So anyway, that's good, clean fun. And it's fun to exploit ARM.
I've been sent by the goons to...
They want us to quit? Okay, fair enough. Well, I'm going to stop this recording.